why is it that when you build a technologically sophisticated telescope that can peer out into the vast depths of space, that you're also looking back in time?
So, all telescopes are time machines of a sort, and that's by virtue of the fact that light, as fast as it travels, and it is the fastest propagating entity that we know about in all of science, it travels about this far, about 1 foot every nanosecond. So if you convert, nanoseconds to miles, and you convert, feet to miles and nanoseconds to seconds, it travels about 186,000 miles per second, which is pretty darn fast, but it's not infinite. So therefore, whenever you're looking at something, you're not seeing it as it is right now. You're seeing it as it was sometime in the past. And the farther away something is, the longer the light traveled to reach your eyes or to reach our telescopes. And telescopes are just eyes of a different sort. They might be sensitive to microwaves in the case of the telescope that I build, radio waves, gamma rays. But just like your eyeballs are two refracting telescopes. They have lenses, they have detectors. And so when we look at the sun, and I'm not advocating as a professional astronomer, never look at the sun with your remaining good eye, but when you look at the sun, you're seeing it as it was. And that period in which it was 8 minutes ago, because it's 93 million miles away. And if you convert feet per nanosecond or miles per second or miles per hour, it takes about 8 minutes for light to travel from the sun. That means that, Jordan, the sun could disappear and we wouldn't see it. And we wouldn't know about it really for at least 8 minutes and maybe even longer. So all telescopes are time machines, even the telescopes embedded in our skulls.
So how far back can we look now with, for example, with the Webb telescope? And that's the newest large-scale deep peering telescope that was launched into space. And how far back have we pushed the horizon of view now?
So yes, the James Webb Telescope was launched on Christmas Day in 2021, and it's been sending back phenomenal images. What makes the Webb Telescope so powerful is not that it can see farther back in time, although it can in a certain sense, but it doesn't have extra magnification, and that's not required to see things that are farther away. In other words, if you use a tiny little telescope like the sort that Galileo used back in 1609 to spot the craters on the moon's surface, you could use the Hubble telescope can also look at the moon, and it won't see things it'll see more detail on the moon's surface, but it won't see farther than the moon because the moon is in the way. Now, if you look where there's no moon, where there's no planet, where there's no galaxies, where there's no absorbing matter whatsoever, then you're seeing back to the creation of whatever light your telescope is sensitive to. Now, visible light has only been around for a few billion years because before that time, because of the universe's expansion, that light has red shifted. It has gone from visible light to infrared light, which is invisible to our eyes, but highly visible. And that is the quarry that the Webb telescope is seeking. Now, if you go farther than the infrared, then you come to microwaves, which is what I study. So the longer the wavelength of light you're looking at, the farther you can go back in time, not because you're impeded by something, but because the very source that you're looking at, has been diminished in intensity and has been reddened by the expansion of the universe, which is a phenomenal discovery that we've only known about for less than 100 years. But because of that universal expansion, we can only see using particular wavelengths of light. And so that's why the earliest light in the universe, there's no light that we could ever see that is more primitive than the cosmic microwave background that I and my colleagues are studying. So the Webb telescope can't see far back in time as we can, but that's really irrelevant. It's designed to do something very specific. Look at the first galaxies that formed, the first stars that formed, exoplanets and other stellar solar systems in our own galaxy. And because of that, it's a phenomenal machine and is unrivaled in its capability.
So what element of let's have you explain what the electromagnetic spectrum is, because people are not going to necessarily know what the relationship is, say, between visible light and microwave radiation. They might not know that those are very varying forms of radiation that is very similar in its essence, and also to explain why the red shift occurs and how that was discovered, I suppose.
Yes. So a spectrum is a characteristic of light. Light has three major properties that we discuss as scientists. One is its intensity, how bright the light is, and the other is the color of the light. And the third is something called polarization, which happens to be my area of subspecialty, not political polarization, but it's an actual useful form of polarization that has to do with the orientation of the electromagnetic field. But all forms of light, now people hear radiation and they get scared. Did a bomb go off? Is there some nuclear reaction? No, it has nothing to do with that. It's just a generic term that scientists call light of different wavelengths. So if you imagine a rainbow, which has an infinite number of colors. People say there's 7 colors, the famous Roy G. Biv we learned about in elementary school maybe, but there's actually an infinite number of colors because the number that describes the color of light is called its wavelength. And the wavelength of light is a continuous number. It can be any number, can have any number of decimal places. So it's a continuous number. Therefore, there's an infinite number of real numbers. Therefore, the spectrum is not discrete in 7 different increments. So now, imagine you go beyond the red color. You keep going to the left of that red color. And actually, this was an experiment done by very famous scientists, and Herschel and even Isaac Newton did similar types of experiments, where they took the sunlight, they refracted it through a prism. So we've all seen these prisms that disperse light. And they had light of different colors coming out at different angles. And that's the property of a prism that causes it to make a rainbow from ordinary white light. And what Newton and Herschel did is they put a thermometer, they went into the red light and they put a bulb of an ordinary thermometer and they kept moving it until it got beyond the red. And then they found that beyond the red color, there was still something coming in causing the mercury to rise in this thermometer. So there was other light of a longer wavelength. They knew about the wavelength of light. And that longer wavelength is what we associate with heat. Now, the opposite side, if you go past the violet side of Roy G. Biv, you come to something called ultraviolet. Ultraviolet is also invisible, and we know about that from the sun. The sunlight produces damaging UVA and UVB radiation. That's not any different except for the fact by its characteristic wavelength. So its wavelength is shorter than violet light. Infrared is longer than red light. And if you keep going in both directions, there's photons and wavelengths of light in all different directions ad infinitum to the high frequency or short wavelength. And it goes to infinity in the other direction. You can have an infinitely long, and that would be called a radio wave. So that's the electromagnetic spectrum. Now, if you've ever listened to a siren approaching, you've heard the familiar Doppler shift. That's interesting. Christian Doppler and Wolfgang Mozart grew up in the same town in Salzburg, Austria. I like to think they're kind of enjoying the irony of that fact that they both have this fascination with sound and its phenomena. And the expansion or dilution of the wavelength of light is exactly the result of a Doppler shift, which is exactly analogous to the increase in pitch and the decrease in pitch that one hears when an ambulance first approaches you with its siren on. That pitch is increased, and that's called a blue shift, meaning it goes to shorter sound wavelengths or it goes to higher pitches. As it goes away, the opposite phenomenon happens, and that's why you hear this characteristic rise as it moves away from you. And that's an analog of redshift. Well, the same thing happens in light.